Okay, after a short break, let's come back. After we give the definition of the area between two curves with the definite integral, according to FTC part 2, if we could work out the antiderivative for the integrand fx small fx minus gx, then we should be able to evaluate the definite integral, and we are able to find the area between two function curves. Right? Now let's check the examples here. Example 1, find the area of the region bounded above by y equals x squared plus 1, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So we need to draw those curves. Okay, we need to figure out which is the greater and which is the lesser function. That's why we still require to draw some simple functions from last semester. You should still recall those functions. So the first one, x squared plus 1. And here they said bounded above by x squared plus 1. So actually that is function f. So I can mark here is 1, and how can we get x squared plus 1? Just shift 1 unit of the x squared of the parabola x squared 1 unit upward, right? Upward. So that will be a parabola looking like this one, right? Looking like this one, parabola. And then y equals x, of course, y equals x, it's a straight line. It's a straight line from 0 to 1. So now let me give the function first. This is my fx top. You can see that fx, the x squared plus 1 is the greater one. And then this is my function g actually, right? Function g is x. Now let me use a different color to shade the region, okay? So top bounded above by the parabola x squared plus 1, and then bounded below by the straight line, this one. And from x equal to 0, what is x equal to 0? The vertical line. That is the x equal to 0, right? This is the x equal to 0. And then x equals 1, x equals 1. So this is 0, when x equal to 0, when x equal to 1. So what is the region S? That will be this part, right? That will be this part shaded by blue. And you will notice that there is no intersection at 1 for those two functions, okay? For those two functions, because you can check that this point on the function g, when x is 1, the y value is 1. But when on the function f, here, this point, when x is 1, the function value should be 2. So there is no intersection at the when x equals 1. Here is this region, right? Then how can we work out the area of this region S? It's pretty easy actually, right? So we have already figured out my function. The top one is x squared plus 1, right? And then the smaller function is x. And here, we don't care about the positive or negative. It's always fx minus gx. What is my a and b? So my a is starting from 0. A and b are x values. A is 0, b is 1, right? A is 0, b is 1. So the area A, okay? The area A the area of the region S, and the region is showing here. So basically you should draw the region first. and this part is the region S. Okay? So A should be the definite integral from 0 to 1 fx minus gx dx. How to evaluate this definite integral is pretty easy. Find the antiderivative x cubed over 3 plus x minus x squared over 2 evaluated at the two endpoints 0, 1, right? So when x is 0, they are all 0. So it should be 1/3 plus 1 minus 1/2, right? Which is 5/6. The final answer is 5/6, and we can check that this part is above the x-axis, so the net area should be positive, right? Should be positive. How to evaluate the definite integral with some simple integrand functions? It's pretty easy, okay? I will be a little quick for this part, okay? I will be a little quick for this part. Now for this question again, okay? For this question again, we can, let me write it in this card. So actually we can take the function f, we can take the function f as which is greater one, okay? Which is greater one. We can take this one as yt, okay? Yt, which we call the top curve, okay? Top function. Because for those two given function, you need to figure out which one is greater than the other from A to B. So we can use the yt, the t as a subscript, capital letter T. And we can give the smaller function g as the bottom function. We call it yb, okay? Yb, which is the bottom function. Bottom function. So to evaluate, okay, so in the graph here, this one is called the yt, the function f, and this one is called yb. So the area, to rewrite the area, we know it's from A to B, fx minus gx. Then we can write it in another way, okay, in a simpler way. From A to B, you can use your top function minus your bottom function, yt minus yb, with the independent variable dx. So here we express the greater function as yt, the top function, minus the bottom function yb, with the independent variable differential dx term from A to B. That is much simpler, okay? And it's easy to understand. You use the top function minus the bottom function. So that is the solution. I typed here. Change the color. So that should be, we can still write the definite integral in this way, okay? In this way. And the curve is given here, right? The curve is given here is much clearer. From the area A is the definite integral from A to B, yt minus yb, the top curve minus the bottom curve with the differential term dx. Now let's see example 2. Find the area of the region enclosed by two parabolas. Y equals x squared and another one is 2x minus x squared. We need to draw this parabola first, right? This parabola. We need to know how to draw the parabola 2x minus x squared. So first let's get y equals x squared a little quick. Y equals x squared, which is this one, right? And so this one is not very clear which one is top curve, which one is the bottom curve, right? So let's rewrite the function 2x minus x squared. You can rewrite it into this way. Minus x squared minus 2x plus 1. So you plus 1, which means subtract 1, then you plus 1 again, right? That is the same. So the reason we write in parentheses is we are trying to get the complete square. So how can you get this parabola? That is you flip you change the direction of y equals x squared. In this way you get y minus x squared. For y minus x squared, you shift 1 unit to the right, 1 unit to the right, and 1 unit upward. Okay, 1 unit to the right and 1 unit upward. So that means the vertex will be 1 1. Okay, the vertex will be 1 1. So will be, if this is 1 here, shift 1 unit here, and then let me change my parabola a little bit. Y equals x squared. So the vertex for this another parabola will be when x is 1, y is 1, so will be here. So the parabola will be looking like this one. So this is the parabola. This is the parabola y equals 2x minus x squared. How can you get this new parabola? First, you get y equals minus x squared. That is, you just change the direction. You just change it means reflect about the x-axis of y equals x squared. Reflect about the x-axis. And then you shift 1 unit. You shift 1 unit to the right. You shift 1 unit to the right, which means you do minus 1 from x. And then you shift 1 unit upward. You shift 1 unit upward. So of course this one will be 1 1, and that is the intersection actually. That is the intersection of those two parabola, because you can check that 1 1 is both on the two parabolas. Okay, 1 1 is on both two parabolas. On the parabola y equals x squared, when x is 1, y is 1, right? When x is 1, y is 1. So this is 1. And in the second parabola, when x is 1, in the second parabola, when x is 1, y is also 1. So that is the intersection. And also 0, 0, 0, 0 is the intersection for those two parabolas. You can check that when x is 0, y is 0. And in the second parabola, when x is 0, y is also 0. So what is the region formed? This is the curve. This is the top curve. What is the expression for this curve? 2x minus x squared. What is the bottom curve? This is x squared, right? So that is the region formed between those two curves, okay? And they didn't specify A and B, right? They didn't specify A and B. What is A and B? So you can check that actually A is 0, B is 1, right? A is 0, B is 1. So now let's write the solution, okay? Or there is another way, okay? There is another way to get the intersection. Just to solve the intersection, if you cannot tell directly from the graph, we don't have 0, 1, okay? We don't have 0, 1 the point. Solve the intersections of the two parabolas. there is algebra way to solve the intersection. So solve the intersection of the two parabolas. You can let x squared, the first parabola, equals to the second one, right? And then it's 2x squared minus 2x equal to 0, right? So you can factorize as 2x x minus 1. So your solution will be x1 is 0, x2 is 1. So when your x1 is 0, the y value is 0. So you get 0, 0, the first intersection. And when x is 1, your y is also 1, you get the second intersection. So the intersection point will be 0, 0, and 1, 1, right? 1, 1. Now let's figure out the area of this region S. Now what is my top curve? What is my top function curve? YT, which is this one, right? Top curve should be 2x minus x squared. That equals this one, okay? Here, be careful. When we call the YT, that is the independent variable x. Then how about the bottom function curve? Bottom function curve is this one, which is x squared. Use the x as the independent variable. So the area A will be evaluated. What is A and B? Starting from A to B, that is x values. So it's from 0 to 1, right? Here they didn't specify, so we need to figure out by ourselves. So it should be yt minus yb minus x squared dx. How can we evaluate this definite integral? It's pretty quick. 2x antiderivative will be x squared, and then minus 2x squared. 2x squared will be 2x cubed over 3, right? And then this function evaluated at 0 and 1. So the final answer will be 1/3, I think. Okay, it's 1/3. So the area of this region will be 1/3. Of course, it's positive numbers. It's above the x-axis. Okay. So it's pretty quick to evaluate this definite integral, but you need to figure out what is yt, what is the top curve, what is the bottom curve, and what are A and B. So that is example 2. Yeah, so the answer is 1/3. Okay, 1/3. So the graph is showing here. Okay, it's more clear than my hand drawing. Now let's check the more complicated case. In the previous situation, we said let function f is greater than g. Okay, let's see this situation. For some value of x, the fx is greater than g. For some other values of x, the fx is less than gx, like this one. Okay, we have the pink color is function f, and we have the blue color is the function g. From to evaluate the area of the region from A to B. So sometimes f is greater than g, sometimes g is greater than f. So how can we deal with this situation? So you can put the absolute value sign to make sure the difference is always non-negative, right? We know the height is still the difference of the two functions, no matter which one is greater, right? So the height is still f minus g. To make sure your height is positive in this case, okay? In this case, we don't need to figure out which one is greater than the other one. So we put the absolute sign, and we can define the area in this way, okay? From A to B, f minus g should always be non-negative, okay? Just add the absolute sign. And here, what does this mean? Fx minus gx. So when f is greater or equal to g, we remove the sign directly. If f is less than g, this is the same case as f is less than g, right? F is less than g, so we put a minus sign, that becomes g minus f. right? That is how we remove the absolute sign. So how can we deal with the area? So here the area of the region between two curves will be S1 plus S2 plus S3. Then we can represent it in this way. With the difference of the two function, put the absolute sign. Okay, put in the absolute sign. Now let's check this one, and the graph is showing here. Example 3. Find the area of the region bounded by the curves. Okay, bounded by the curves. Y equals sine x. Y equals sine x is the blue one. Okay, and y equals cosine x is the pink color. From 0 to pi half. Okay, from 0 to pi half. We can draw those from 0 to 2 pi to show those two curves, right? What is sine? This is sine from 0 to 2 pi, right? From 0 to 2 pi. This is y equals sine. And what is cosine from 0 to 2 pi? Let me use a different color. So the blue one shows y equal to cosine, right? And we only care about when x starting from 0 to pi half. 0 to pi half will be this one, right? Will be this one. So you only take the part, then we zoom in this part, we zoom in this part, right? So we zoom in this part. And here the blue is sine, the pink is cosine, okay? So from 0 to pi half, you will notice that from 0 to 2 pi half, sometimes cosine is greater than g, sometimes sine is greater than cosine, right? So here, actually from 0 to pi half, you will do cosine minus sine. And from pi over 4 to pi half, you will do sine minus cosine, right? Let's solve a little quick, okay? Let's solve a little quick. So the area A, according to our formula, will be from A to B, and my function fx minus gx, right? My function fx minus gx dx. And you can write your function f is cosine, your function g is sine. So everyone should be familiar with the trigonometric function curves. And then let's check from the graph. From 0 to pi half. By the way, the pi over 4. The intersection of sine and cosine will be this point, right? What is the intersection? Let's solve the intersection. Intersection will be you let sine x equal to cosine x, but your solution for the x should be between 0 and pi half, right? Sine x equal to cosine x, you can divide by cosine x, which you get tangent x equal to 1. What is the tangent x equal to 1? So the solution will be x equals pi half with some special values you memorized about the trigonometric functions. So x will be pi half. What is the sign? What is the function value here? The function value sine pi over 4, cosine pi over 4 will be root 2 over 2. So the intersection point will be pi over 4, sorry, pi fourth root 2 over 2. Right? That is the intersection. So we can divide it into two parts from 0 to pi over 4, pi over 4 to pi over 2. So from 0 to pi over 4, which one is the top curve? Top curve will be the pink color, which is cosine x. So in this part, f is greater than g, you just remove the absolute sign directly. So you get cosine minus sine directly dx. And then plus the definite integral pi over 4 from pi over 4 to pi half. So in this case, the sine will be greater than cosine, right? So which means gx is greater than f. So that will be the absolute value sine will be gx minus the fx. And by the way, here the answer of course is not 0, right? The area A, the answer is not 0. That will be the sum of the area A1 plus A2. It's positive. It should be a positive number. Now let's work out. It's pretty easy to work out the antiderivative. Cosine antiderivative will be sine. Minus sine antiderivative will be cosine. So this antiderivative, this function evaluated at 0, pi over 4, and plus the second part, sine antiderivative will be minus cosine. And minus cosine antiderivative will be sine. So it's both minus from pi over 4 to pi half, right? Let's recall some special values. So sine pi over 4 plus cosine over pi over 4, sine pi over 4 plus cosine pi over 4 should be root 2 over 2 plus root 2 over 2, so you get double. And then minus sine 0 gives 0, cosine 0, which is 1, right? Cosine 0 is 1. Sine 0 is 0. That is the first part. And for the first part, you can put the subtraction outside, okay? So that becomes cosine plus sine, okay? So inside plus becomes cosine plus sine. So cosine pi half, which is 0, right? Cosine pi half is 0. And sine pi half, which is 1. And then minus, here becomes cosine plus sine, okay? Cosine pi over 4 plus sine pi over 4, which is still root 2. So what is the answer for this one? Should be twice root 2 minus 1. And actually you will check that the region S1, we just call this region for the area 1 is S1, this region is S2. Regions, you will notice that those two regions are symmetric actually. Regions S1 and S2 are symmetric. So regions S1 and S2 are symmetric. You can just calculate one of them, then multiple by 2. They are symmetric about the vertical line. X equals pi over 4. So one student asking in the demo, explain the answers we got. That is some special values for the trig functions. Sine pi over 4, cosine pi over 4, right? You just do, it's still the big, this is the big function fx, fb minus fa. You just do the calculations, okay? Do the calculations by yourself. So that is example 3. We put the absolute sign if the case from A to B, sometimes f is greater than g, sometimes g is greater than f. So that is the same, right? That is the same answer I typed here. You find the antiderivative. Okay, find the antiderivative. By the way, 1 over root 2. 1 over root 2 is the same as root 2 over 2. It's the same. I just rationalized the denominators. Okay, denominators. Now let's look at the curve in this way. Okay, we are going to summarize the area when we're looking at the variables in different ways. So area between the curves, if we are using the variable y, if we are using the variable y, you will notice that this time the rectangle is in the horizontal way, okay, in the horizontal way, and the width of the rectangle, the previous one, okay, think about the previous one. The previous one, this is the way we form the rectangle, right? The equal weights will be the delta x. Now, if we use the variable y, then the equal weights will be delta y. Then what is the height of this rectangle? So in this way, that will be the difference of the two function curve, but we express using the independent variable y. So in this way, we will call the gy as the left function curve, but now my dependent variable becomes x. I will call xl. And the fy is the function curve on the right side, okay, on the right side. So if I'm using the y, sometimes it will be more convenient to use the variable y, okay, use the variable y to do the integral. But if we use y, so that will be the left function curve, which is expressing in y, okay, expressing in y, so the lower and the upper limit becomes c2d, okay, c2d. So if you rotate this one 90 degrees, that becomes the one we did previously. And this is a traditional one. We usually do that, right? We usually do that from A to B, and sorry, from A to B. So this is delta x, this is the delta x, right? So if we rotate this original one by 90 degrees, then that becomes this curve. But now it's about y, so the lower and upper limit in the definite integral becomes c and d. It's about the y values, y value. So the difference of two function curve will be the right side, okay, will be the right side curve minus the left side, which gives the difference. That is the height of each rectangles. So will be the right function curve minus the left function curve, but this time with the independent variable y, right? What is the previous one we did? What is this one we did? This one we are using the independent variable x. That is from A to B, the top function curve minus the bottom function curve, right? And with the independent variable x. This is the usual one we used. So that is about the independent variable x. So this yt and yb, that is the expression using x. Okay, that is the expression using x. So don't be confused with those two. Okay, then this one is we are using the independent variable y. We use the left function curve minus we use the right function curve. Subtract the left function curve and using the independent variable y. So, am I speaking so fast? So the difference of those two, okay? The difference of those two are just the variable, the independent variable we choose. This is the old one, okay? This is the old one. We usually use the notation, right? We use the top function curve minus the bottom one. Then we rotate, okay? We rotate this one by 90 degrees, so you get the horizontal rectangle. You get a horizontal rectangle. So this one is the right function curve. Subtract the left function curve, but they all express using the y, okay, using the y. So any questions so far? And this is a case when the intersect at one point. It's the same, okay? It's the same. You use the right function curve. What is the limit? Yeah, this is the case when they intersect, okay? This is the case when they intersect from C to D. From C to D. If they have several intersection between C and D, so you can do in this way from C and D. If you don't know which one is greater, which one is smaller, you can use this one. You can put the absolute sign. You can put the absolute sign, right? To make sure, like the one we did for the x-axis, okay, when we're using the independent variable x. All right, here is a quiz to apply the formula, okay? To apply the formula, you need to figure out C and D using y, okay, using y. And you need to figure out what is your right function curve. What is your left function curve using the variable y, okay? Using the variable y. So the right function curve will be x equals root y from here, right? From the graph. This is the right function curve. And then the left function curve will be y squared minus 1. Here we should use y. We should use y because it's easy to figure out the bound, the lower and upper limit for y. It's from 0 to 1. Okay, so I'm going to send this one as a quiz for 5 minutes, and I can extend it for another 5 minutes. So let's try the quiz.